All right, this is going to be the video for the first half of 16.2, which is about line integrals. And this is a pretty, I would say, hard to wrap your mind around concept at first. So we're going to definitely break this into two parts. We'll cover the main idea here in the first part. There's a lot going on. And then there's kind of a second way that we do things. And for that one, we'll save that for a second video. Okay. All right, so what is a line integral? Now that we've talked about vector fields, we're going to sometimes work with vectors fields, and sometimes we'll work with regular scalar multivariable functions. All right, so just as a reminder about integrals. Integrals sum things, right? So we first saw integrals in the context of finding area under a curve, where we said, all right, we could cover a area under a curve with rectangles, and then sum those rectangles up, heights times widths, right? The widths would be changes in the x variable in the domain. And then the height would be established by the function value at that particular x value for that slice. And then we smooth this into an integral, right? When we take an infinite number of these rectangles, and this just becomes f of x dx, where f of x is the height. And then in chapter 15, we opened this up to, okay, now we don't have to have a one-dimension domain. We can have two dimensions domain and have heights above all of those different things being set by a multivariable function where z is a function of x and y in the domain. And then we can use a double integral to sum that over the entire region in the domain. And that two-dimensional area times the height gives me a volume, right? But then we said what we should really be thinking of integrals as is summing the integrand, whatever the integrand is, right? So if we have an integrand, which is scalar numbers, like different y values here, and we sum those over some piece of the domain here, which is, let me use a different color here for the domain, which is a single variable here, x, then we're summing these values over this domain, right, with this integral. Okay, and then we had a double integral, which said that, okay, we have an entire surface of values for different places in the 2D domain, right? And then we want to sum those all over here. So I'm summing all of these values basically on a surface over a region in the domain with a double integral, right? And the values we're summing are the integrand, the values of the multivariable function for those places in the domain. And then for a triple integral in general, we have now a three-dimensional domain, right? So a 3D domain. And then we have some multivariable function of the x, y, and z of those domains. Maybe it's air pressure or something, and that's what these blue numbers represent. And so we're summing all the blue numbers inside that 3D domain with a triple integral, right? So most of the rest of this chapter, we're going to be using integrals to sum up quantities. But they may be scalar quantities like these, right? Or we might be summing up vectors, right? Which is why this chapter is called vector calculus. Mainly it's about summing vectors, but sometimes we'll sum vectors up. Sometimes we'll have integrands which are scalars. And we'll see both of those cases here in 16.2. All right, so what we're going to do in 16.2 is say, what if I want sort of a mix of those cases, right? If you think about a single integral is summing along a path, right? That path basically is just the one variable. We just take like along the domain, which we can only vary in one direction. We want to sum these values over that domain. Okay. The double integral has the summation over a 2D area in the domain of the integrand values. Right? But what if instead of summing over the entire 2D area, I don't want like an entire sheet of numbers here. What if I just want the numbers along a path through that surface, right? So I just want, say, these circled numbers here. I just want these numbers added up. How would I do that? Well, that path is not really two-dimensional. In other words, in the domain down here, I have a 2D domain, right? It's true that the domain is 2D, but I really want to follow a 1D path through that domain, and then I want to sum up all the values of the multivariable function along that path. So that is called a line integral. We really should call it a curve integral or a path integral, right? But it has traditionally been called a line integral. But what it means is that we're going to sum up values of some sort of an integrand, but we're going to sum it up over a path, but that path is potentially a curved path through the 2D domain, okay? So the thing that's tricky about that is that we're going to have to find a way to integrate along this curve, right? And we can't resort to a double integral because we don't want an area. So we're going to still have to be kind of like this. We're going to have a single variable that we're integrating over, right? But it has to follow a curved path instead of just a line. So here's how we do that. We take the curve, right? We take this curve here, and we're going to parameterize that curve, okay? Meaning that we're going to somehow express it in terms of a parameter t, so that I go from like t equals a over here along the curve to some other point t equals b, and then I'll integrate all these values along that path. We'll be back to something like this, except we're going to be doing an integral of the multivariable function along the parameter path. Okay, so we'll have to parameterize the curve in the domain. Right, so that means we should, I think we need to review what we know from chapters 12 and 13 about parameterizing curves, and then we'll show how we'll actually do a line integral. So here's some things that we learned earlier in the course about parameterization. If we have a circle in 2D, right, you want to go clockwise or counterclockwise around the circle, you can just replace x with the radius times cosine theta and y with the radius times sine of theta, okay? And then just if you allow the t parameter is essentially then the angle. So at this point, t is equal to 0. Here, t is equal to pi over 2. And here, t equals pi. And if you want to go all the way around the circle, you have to make t go from 0 to 2 pi. Okay, so that's a parameterization 2D if you're going counterclockwise around the circle of radius a. If you want to go the other direction for some reason, sometimes we'll see later in the chapter where we have to be careful about the directions. Then you either have to make one of them negative or you have to swap the sine and the cosine, right? All right, if you want to parameterize an ellipse, then all you have to do is make these two radiuses different. And by the way, there's a typo here. That should be sine t. So you just take a circle parameterization. X is a cosine t, y is a sine t, but you can just have a different multiplier if you have a different half-axis length in the other direction, right? And then you're parameterizing the ellipse. All right, so we can parameterize a circle. We can parameterize an ellipse if we have a curved path in the domain. If we have lines or line segments, first let's talk about a line. If you're parameterizing a line, then the general form is that we're going to use the curve r as a function of the parameter. It's just going to be the position vector, and that is some initial point. So maybe we could call it r0. Let's call it r0 is a vector from the origin to an initial point, and then we have to mix in a parameter times v, where v is some vector that's in the direction. So this would be some vector that's in the direction of the line, okay? And then in that case, if we want the entire line, the parameter goes from negative infinity to infinity, right? If instead we want to parameterize just a line segment, then we have t just go from 0 to 1, and we have a little bit different structure, right? We have that the position vector, r, is 1 minus the parameter t times the initial position vector plus the parameter times the position vector to the end. So we have a position vector at the start, position vector at the end, and basically what happens is as t goes between 0 and 1, we start at the initial point and we're slowly blending out the initial point and in the final point until finally we're at the end point. Right, so we have parameterizations for circles, ellipses, lines, and line segments already. Right, and all this is in 2D in a 2D domain. Okay, there are occasions when we're going to do line integrals or path integrals, but where the domain is 3D. Right, there's no particular reason why the multivariable function has to be a function of only 2. We will often do that because it's easier to sketch, but you could actually have any number of variables in the domain. So let's just talk about parameterizations that are circular in 3D. Common ones are if you have a circle path, right, but it's just at some fixed z, like z equals 3, well then you can use a circular parameterization for x and y. X as a function of the parameter t is a cosine t, y is b sine t, and then you can just make z equal to some constant and parameterize from 0 to 2 pi to go once around the circle. Another common one is a helix, where we have a spiral that's slowly going up. So if you use a circular parameterization for x and y, and then z is just equal to the value of t, as t increases, then the z just steadily increases, so the circle spirals upward like that. Right? So those are some common parameterizations of curves that we'll encounter. And they're common not only because they're easier to deal with than more general curves for our analysis purposes, but also these shapes also come up frequently in engineering and physics problems. All right, so one more thing before we actually talk about the setup for the line integral itself. It's based on arc length. So back in chapter 13, we explored arc length, and we concluded that if we wanted the length along some curve, some space curve C, from parameter t equals a to parameter t equals b, right, we can always find the tangent vector. Actually, t stands for the unit tangent vector, unit length, and that is defined this way. We take the tangent vector, that's what this vector is, r prime. In other words, we take the position vector, take the derivative, that's called the tangent vector, and then if you normalize it, you end up having something which is magnitude 1, so that gives you the unit tangent vector, okay? So if you just want to know something about the direction that you're traveling, you use the unit tangent vector if you're not caring about like the magnitude of the change, right? But if we're actually trying to find the arc length, then instead of using the unit tangent vector, we just use the unnormalized tangent vector, which is just the derivative of the position vector, r prime. And if you take the magnitude of that, it's like the little length here for an infinitesimally small portion. So if I want to find the arc length, what we said back in chapter 13 is, I just use an integral to sum up over some region of the parameter from t equals a to t equals b, the magnitude of the tangent vector. And that gives me the arc length. Okay, so what we're going to do for our path lengths, or for our lengths here, is we're saying, take you back to this picture, we're saying that we want to go along a path, but instead of just taking the length of the path, we don't want to just sum up the length, we want to sum up the value of some function. Okay, so all we're going to do is we're going to take that arc length integral, and we're going to insert in here a multivariable function that is the thing we're summing. And in fact, we'll have to express that function as a function of the parameter. So we're going to have to take whatever the equation is for x's and y's and convert the x's and y's into their functions of t, right? So that everything in the integral will vary with t, and then we can integrate that structure. So that gives us what's called the definition of a line integral for a scalar function. If you're integrating a scalar function, values of a scalar function here along some path, right? That's this part, the integrand. If you want to integrate that along a path, then you have to parameterize the curve, right? And with that parameterized curve, the little length is going to be the magnitude of the tangent vector, of the position vector to points on that curve, dt. And then you just integrate that from some starting t value, like t equals a over here to t equals b. All right, so that's really all that's to it. It's a little weird to think about it, and it's actually it's harder, I think, to conceptually as and understand it than it is to actually conduct the integrals, because unlike in chapter 15, when we do this integral, it's a single integral. We're even going to be able to evaluate them with Math 9. It's pretty straightforward once we get it set up. Okay, so this is called the line integral along a path C for a scalar function, because we're integrating a scalar function here. And of course, what that would do is give me a scalar output value, right? Because it's a sum, basically it's the sum of all these numbers. It's like a sum of an infinite set of numbers here, which are the output values along the path, all right? But we said that we don't have to have a scalar function as this thing that we're integrating. We could have a vector function, right? So let's say that I wanted to sum something along here, this path, but I wanted to sum, but the thing I'm summing is a vector. So this is actually incorrect. I should write this as some sort of vector field. That's a function of x and y of some kind, right? All right. So, or a function of, right? All right. So although I've drawn it up in the air, everything really would be down here on the xy plane if I have a two-dimensional domain. But there's a vector. So what we're saying is that every xy, there's a vector, right? And I'm going to take some sort of curved path through the domain, and I want to sum up the vectors. So how do I sum up vectors? Well, because we're moving in a direction, we're going to define this. And this is arbitrary to define it this way, but this is the way it's defined. We're going to take not the entire vector, but we're going to say if at this point on the curve we're moving in this direction, defined by the r prime, which is the tangent vector. Then I'm going to just take the percentage of this this particular vector that's in the direction of motion, and I will sum that up. So I'm summing the projections along in the direction. And to get a projection, we can do a dot product, right? If you take a vector f and you take the dot product with the direction vector in the direction of the tangent vector, that will give you the fraction of the vector, the force field, if it's a force field, in the direction of motion along the curve. Okay. Now, for really astute students, you might be remembering way back when we said we use a dot product to project, you have to take the dot product with a unit vector, right, in the direction, right? But the reason why we're going to take a dot product with just the original tangent vector instead of the unit tangent vector is because we also want to have this little length factor in, right? We have to have a length when we do our integration. So by doing f dot r prime, we're getting the length piece and we're getting the projection piece all in one. So that gives us this formula here. If you're doing a line integral along a path in the domain of a vector function, then you evaluate the dot product of the vector function and the tangent vector at any point along the curve for a parametrized curve. Okay, and note, since we are taking a dot product here, right, we're really finding the magnitude of this length, right? This dot product will produce a scalar number. So we still get a scalar result, even with a vector. The way I think of it is this. Let's imagine that you had a pathway through, say, some water, like these blue vectors represented water, okay? And you wanted to figure out how much force am I going to have to use to push my way through this water. Sometimes I'm going in the direction of the water, sometimes going away from the water, so I have to fight against it. So if I happen to be moving in the direction where I'm going with the flow, then I'm going to be summing up positive things into my total amount of effort I had to put forward. But if I happen to go to some place where I'm going against the flow, and I'm moving in this direction, and the vector field is in the other direction, for example, then that means that I would have some negative things that are added in there, and I might have a total like it pushes me along for part of it, but then it fights me along for other parts of it, right? So and I need to know, well, what fraction of it is in the direction I'm going right now, because that matters. If I'm going with the flow, I have a positive addition to this integration sum. And if I'm going against the flow, then I have a negative addition. All right, so that's the idea behind integral. So we have an integral along, actually, let me go up to this screen where we summarize it. We have a line integral for scalar functions. And in that case, we use this structure where the integrand is a scalar multivariable function. And we have line integral for vector functions. This is just a vector function, where we are defining the integrand is the dot product between the vector function and the tangent vector direction. Okay. Now, although it's much harder to picture, in this case, I've just drawn situations where you have a 2D domain. You can actually have any number of functions here, or any number of input variables. So you could have a 3D domain, you could even have a 4 or 5-dimensional domain. Of course, it gets really hard to picture at a certain point, okay? So we'll do an example here in a second that has a 3D domain for this case. Okay, what I want to do next is just do 2 examples. I'm going to do one example of a scalar and one example of a vector, so you can see how it works. And you'll find that although it might be hard to conceptualize what's happening, the computation of it is not that hard. Once we get the parameterization, sometimes the parameterization is the hardest part. Okay, so this says, evaluate this line integral. We have a line integral of xy to the 4th ds, so ds is a little distance along the curve, where the curve C is the right half of the circle x squared plus y squared equals 16. All right, so first of all, the integrand here, xy to the 4th, is not a vector, and that means we have a scalar function case, so we're going to use this version. That means we're going to have to come up with some parameterization of the curve so that everything's in terms of the variable t. We'll have to find a position vector for moving along that curve and find the derivative so that we can find the tangent vector and find its magnitude. And then we'll have to take the original multivariable function and replace the x's and y's with t's, okay? So to start with, let's graph the curve so we can parameterize it. Here's a graph of the curve here. It's a circle of radius 4, but it says only the right half. So we're going to interpret that as the positive y or x portion like this, okay? I'll pick a direction to go. Typically we go towards positive angles, right? And we're going to parameterize. So since this is a circle, I'm going to use the parameterization that x is the radius 4 times cosine t and y is sine t, where t is understood to be the angle. And then to parameterize this entire curve with a smoothly increasing value, we're going to have t start out at negative pi over 2 and then go around here until the angle is positive pi over 2. So that'll be the region we parameterize over. Okay, so we've got a parameterization of our curve in the domain, and that means that we have a position vector. So the position vector to any point on that curve, in other words, if I draw in a little position vector here, r, okay, then that would be that the x component is 4 cosine t and the y component is 4 sine t. And I need the position vector because I have to take the derivative of that to get this vector, the r prime, okay? So the derivative of cosine is negative sine, so the x component is negative 4 sine t, and the y component is 4 cosine t. And now that I have an expression for the x and y components of the tangent vector, r prime, I can find the magnitude by taking the square root of x squared plus y squared, right? And when we get to this stage, right, you could factor out the 16, getting cosine squared t or sine squared t plus cosine squared t. But sine squared plus t plus cosine squared t is 1. So this is just the square root of 16, which is why it's 4. So for this particular curve, the tangent vector always has a magnitude of 4. Okay, and so now we just need to put everything in the function. So we have the dt, right? We have the position vector here, or sorry, the tangent vector, which is 4. And then we have to take the original multivariable function, which is x y to the 4th, and we have to substitute things for x and y. So I'm going to put 4 cosine t in for this x and 4 sine t in for the y, because that was our parameterization. So we end up with 4 cosine t, that's the x, 4 sine t to the 4th, that's the y to the 4th. And then we just integrate over the value of the parameter, which is from negative pi over 2 to pi over 2. So this is hard to read, but it says negative pi over 2 to pi over 2. And that's the setup. We're back to having a single integral because we're just evaluating over one parameter. So we won't typically spend time on evaluations here, but if we did, we could just do a math 9 in a calculator like a TI-84 to get the result is this. And what this represents is this is the sum of all of the integrand values of, or for these particular x-y pairs, all of them on that curve. All right. Okay, so that is a line integral for scalar functions example. I wish they called them path integrals because this is not a line, but we're integrating along this curved path. Let's take a look at a vector function case. So a vector function case, we're going to have to use the other one. This would be asked something like this. Evaluate, typically there would be a vector line over that and probably over this as well. So we want to take the integral of some vector function over a curve C. And they gave me that the vector function is defined by, now this actually, there's a typo here. This should be a z here because I see an x, a y, and a z component being included here. So we have that in terms of our rectangular coordinate system x, y, and z. And then we want to sum that the components of that force that are in the direction of motion along this curve. And instead of making us parameterize it, they just went ahead and gave it to me that the position vector is t squared for x, t cubed for y, t squared for z. And we want to cover the region where the parameter goes from 0 to 1. All right, so this integrand is clearly a vector, so we've got the vector case. So we're going to use this version of the line integral formula where we have to find that tangent vector, but then we're going to take the dot product of the vector function with that, and then integrate that over the parameter region. Okay, so we've got the r vector here. We could take the derivative of that term by term, so the t squared becomes 2t, and t cubed becomes 3t squared, and then 2t. This is the tangent vector. Now I'm not taking the magnitude now because instead I'm going to end up taking the dot product with this vector, right? The dot product with this f vector. Before I do that, though, I'm going to convert it also in terms of t, right? Right now we have it written in terms of x's and y's and z's. So what I'm going to do is take all of these x's are going to be replaced with t squared. So this x here, right? Any y, so this and this is going to be replaced with the t cubed, and the z is going to be replaced with the t squared. So that's what I'm showing happening down here. This is, x plus y, y minus z, and z squared here, right? So if you kind of multiply that out and simplify, you end up getting this. It's the vector t squared plus t cubed for x, t cubed minus t squared for y, and t to the fourth for z. So then the next thing we have to do is take the dot product of those two things. So the dot product just means that we multiply this times this plus this times this plus this times this. So if you carefully do that, and then you simplify, you end up getting this result. And that is therefore the entire integrand that we need. So we're just going to integrate that over the region for the parameter, and they told me to use a parameter region from 0 to 1. So if you integrate that, you end up getting 17/5. Okay? And what that represents is, in this force field, as you go through this in 3 dimensions, actually this is a 3-dimensional force field, as we follow this path by r, we're summing up the component of f that's pointing in the direction we're currently traveling as we go from t equals 0 to t equals 1. All right? All right, so I think that's where we're going to stop this first part, because the second part in the lesson has something a little different. So in the class, I'll announce which homework problems you can do up to this point, and then may have to watch the second half video before we can finish it. That'll finish the first part video.